All right, once again, part one, right triangle trigonometry. So we're finished with algebra, at least pure algebra. Algebra will always be incidental to the problems we do. But as far as a specific study of algebraic relationships, that part of the course is over. Now we're into trigonometry. So the task is going to be to find values of trig functions and solve right triangles. And some definitions. First of all, trig ratios. If I've got a right triangle, I can break that up into three sides, A, B, and C. Now, with respect to one of the angles in that triangle, one side is the opposite, one side is the adjacent, and the side opposite the right angle is the hypotenuse. Always only one hypotenuse, and it is always the longest side. So the trigonometric ratios are ratios of these sides to each other. Trigonometric functions are functions with the input of an angle and the output of a ratio. So again, the ancient Greeks understood that as I change that angle, the sides ratios to each other change in a predictable and functional way. All right, so let's talk about those trig functions. First of all, the sine. And again, there are three. These are considered the main three trig functions. No special reason for it. They were just the three that were picked first. So the sine function is abbreviated sin, and you have some angle as the argument. So the sine of some angle alpha is going to equal that angle's opposite side divided by the hypotenuse. And then the cosine is abbreviated cos, and again, it always has an angle as an argument. And it's going to be the adjacent side divided by the hypotenuse. And then the tangent, the last of the three primary trig functions, is the opposite divided by the adjacent. So there are six total. Again, you remember my argument. You've got three sides and you're comparing two. How many ways do you have to pick the first one? Three. How many ways do you have to pick the second one? Two. 3 times 2 is 6. There are 6 total, but these three are considered the primary three. Now, there are a lot of memory devices here. So the first one, and the one I like, is SOHCAHTOA. So the sine is the opposite over the hypotenuse, the cosine is the adjacent over the hypotenuse, and the tangent is the opposite over the adjacent. So that's old Indian chief, SOHCAHTOA, smoking a peace pipe in his little wigwam and thinking about triangles. So what you think about when you smoke a peace pipe? Okay, so there's another method, and this one was the preferred method of a former math teacher here. Yes, ma'am.
I have one more fan. Do you want it? It's a floor fan.
Sure.
But you could set it up sometime.
Sure, that'd be great. Thank you. Yeah, I appreciate that. So there's one other technique that was a preferred technique for a math teacher here. Mr. Greenwell, I think, was a math teacher here back in the 90s, 80s, and 90s, and even the 2000s. But he used this. Some old hippie caught another hippie tripping on acid. Whatever works for you. I don't care what memory device you use. So these are the three primary. These are the ones that are on your calculator. These other ones are not. So the three that follow, these are called the reciprocal trig functions. Not to be confused with the inverse trig functions. So when I say inverse trig functions, thank you, Jennifer. That'll be very helpful.
It was kind of dusty, but
That's okay.
have at it.
Thank you so much. Yeah, it will. We're going to use this bad boy. Well, I've got my fan here in the corner, but I'll use this one. Maybe to help circulate the air or something. Okay, so cosecant. You would think cosecant would be the reciprocal of cosine, wouldn't you? Wrong. It's a reciprocal sine. And it's abbreviated CSC. Always has an angle for an argument. And you remember the sine was the opposite over the hypotenuse, so the cosecant is the hypotenuse over the opposite. Secant. You think the secant would be the inverse of the sine, right? Wrong. Inverse of the cosine. It's abbreviated SEC. Always has some angle as its argument. And you remember the cosine was the adjacent over the hypotenuse. So its reciprocal here is the hypotenuse over the adjacent. And then cotangent, well, this one is the inverse of the tangent, as you would expect. COT is how we abbreviate this one. And remember the tangent was the opposite over the adjacent. And so this one is the adjacent over the opposite. So for this one, the memory device, and this was John Jones's creation. Choshakao.
What are the letters of the last one? COT?
Yes, COT. Cotangent is abbreviated COT. Choshakao. And another thing to remember about these is the cosecant is the sine to the -1 power. Now, be careful with this. In fact, you know what? I'm not even going to write that because there's a notational inconsistency we're going to run into later that makes that disadvantageous, and you'll know it when we see it. But know that this cosecant is the inverse of the sine, the secant is the inverse of the cosine, and the cotangent is the, and we're talking multiplicative inverse here, not functional inverse. So cotangent is the multiplicative inverse of the tangent. In other words, take the ratio and just flip it. You multiply them together, you get 1. All right, once again, you got sine, cosine, tangent, SOHCAHTOA. You got cosecant, secant, cotangent, choshakao. So the reciprocal functions are considered to be those last three. So they're considered to be the cosecant, the secant, and the cotangent. Now the inverse trig function is a whole other ballgame. So with respect to those first three, we'll have inverse trig functions that undo what the function does. So the reciprocal functions are these, but the inverse trig functions. So you've got sine of alpha, you got cosine of alpha, and you got tangent of alpha. And in every case, you got a bag of angles and a bag of ratios. And these functions map angles to ratios. So these map some angle to some ratio. The trig inverse functions, the inverse of the sine, cosine, and the tangent, do the opposite of that. And they're indicated with this little -1. That's why it's a bad idea to use -1 to describe the reciprocal functions. Because you've got this little -1 superscript after the function. It doesn't mean take it to the -1 power. It means the functional inverse. And then cosine is going to undo that. And it maps it back to an angle. Tangent inverse. And these are the only commonly used trig inverse functions. So those are described as the inverse trigonometric functions. They undo what the sine, cosine, and tangent do. The sine, cosine, and tangent map an angle to a ratio. The sine inverse, cosine inverse, and tangent inverse map a ratio back to an angle. So they take a ratio from a triangle and they tell you what the corresponding angle must be for that triangle to work. This making sense? Or am I Charlie Brown talking again? That's where you hear a teacher like this. Wah, 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 wah. You ever go into that mode? Yeah, me too. My wife calls me on it too. She's like, "What did I just say?" I'm like, something about work and. Yeah. So anyway, this is your book's graph of the sine, cosine, tangent, cosecant, secant, cotangent. They got a nice little diagram here. They use the angle theta, which is another Greek letter you'll see a lot in this section. Looks like this, capital theta. Some other Greek letters you might see are beta, looks like a B with a funky tail. You might see phi, which is pretty cool. Several others I'll use. I'll try to help me remember and I'll explain what they are that we're using. But anyway, you don't have to write this down. This is in your book. You can consult it if needed. So measures of deflection. So if I were to rotate, a long time ago in the ancient world, they thought about deflection as a measurement. It's an important thing to measure, right? I mean, if you're building the pyramid, you need to be able to measure deflection because you want things to square up with each other, right? So anyway, think about deflection. If I rotate, you see how if I rotate through an entire circle, I wind up where I started. So that's just like a logical unit of rotation. Now, there are two primary ways to describe this. The first is with angles. So, and this again comes from the Babylonians. You ever think to yourself 360 degrees, that's a weird arbitrary number to have in a circle? Well, it's also a multiple of 60, which is the base number of the Babylonian number system. And 3 and then also 6 were very special numbers to the Babylonians, relating to their religious beliefs and so on. So if I were to take a circle, and I were to inscribe polygons, the least number of sides I can inscribe is 3. That's not a very good model for the circumference. Do you agree? So if I were to take all the lengths of these sides, it would be an extremely rough estimate of the circumference of this circle. Now, the Babylonians did not have pi, but they used 3. And in fact, in the Bible, it uses 3 for pi, which is pretty close. Not exactly right, but close. So if I were to inscribe a 4-sided polygon, you see how that's a better approximation? But still not good, but better. So if I continue this process and inscribe larger sided polygons, regular polygons, and of course mine are a little irregular, but imagine they're regular. Do you see how when I get to 6, it's a much better approximation than any of the previous ones? So this is where the 3 for pi comes from. If I were to use this to model the circle, then I would get 3 instead of 3.14 and so on for pi. Now think about this. If I break this up into triangles, how many triangles do I have, Ian? Good. And so let's say I'm going to assign some arbitrary number to the degrees of rotation for each of these triangles. What arbitrary number do you think a Babylonian would use? 60. That's their base, right? Just like we would use 10. And so if I let this be 60 degrees, 60 degrees, 60 degrees, 60 degrees, you see how I get 360 degrees for the circle?
Yeah.
So this is not settled history. This is my speculation. So I speculate this is the origin of the 360 degrees. It's arbitrary. If we were to encounter aliens from Venus that were intelligent, they would most certainly not use 360 degrees for the circle, because there's nothing built into the circle that makes 360 a logical number to use. Just arbitrary. Pick 14, 275, 3 million. Arbitrary. But radians, and this will always be your first and best language of deflection. So, you know, like if you learn a second language, you're never going to speak it quite as well as first, at least not usually. So I'm going to teach you a new way to describe deflection, but it will always be that second language. And so as a consequence, you'll always probably default back to degrees, and that's okay. But I'm going to teach you a new way, and this is one aliens would know. It's called the radian. So the radian measure is the arc length divided by the radius. So they measure the same thing, but for the radian, that is the arc length swept out divided by the radius. So arc divided by radius. And if we have a unit circle, well, the radius is 1. And so the radian is just the arc length for a unit circle. Now, let me show you. To have an angle, you need 2 rays and a vertex. So the way I've set this one up, got this. So to describe this, I could use those arbitrary numbers of degrees, but you see how I'm bringing in something from the outside when I do that? But if I were to use radians, then I pick any points that are equidistant from the vertex. So this has to be the same, these lengths. And you could do that with an old school compass. So that length that is swept out is called S. And I'm talking about from there to there. It should be like snaps to a line. That's not what I wanted it to do. But anyway, so that what I've highlighted is the arc length S. And then this would be the radius R. And so I could describe that angle alpha in terms of radians as S divided by R. Do you see how that's not bringing anything extraneous into the situation? I'm just using things that are built into the angle to describe its deflection. So this is why if we encountered intelligent aliens, they would understand this. They would know what we were talking about. They would have to. They're space-rank species, especially. So radians versus degree, they are both ways to describe deflection. Radians are just absolutely ubiquitous in high-level mathematics. Starting with Calculus 1, you will almost never see degrees again. It's just a more nuanced and logical way to describe deflection using the radian. The radian is a unitless measure. There is no unit for the radian. If you think about it, no matter what I measured those in, inches, feet, miles, you see how they would just cancel out and there would be no unit because I'm dividing one measure by another. So radians are considered a unitless measure. It's an important mental note to make because you're not going to see, any little symbol like you would with degrees to clue you into the fact that it's a measure of deflection. What clues you in is it's usually multiplied by pi. So you'll see things like 5 pi over 4, and ooh, that's a radian. And also if it's the argument of a trig function. Of course it's a measure of deflection. Colin.
What's the word that's at the bottom left of that?
Vertex. Oh, this right here?
No, yeah, the
Vertex?
Yeah.
Ray 1, ray 2. The 3 parts of an angle. So using only those 3 parts, I can describe the deflection of that angle in radians as the arc length divided by the radius. And again, it's typically multiplied by pi. It'll be something times pi divided by something. And so if I were to measure the whole circle in the same way, and instead of using this arcane system of the ancient Babylonians, I were to use the much more logical system of the radian. So if and this is 1 unit of radius, if I go all the way around, you remember that I've 2 times pi times r. You remember this formula? Formula for the circumference of the circle. So that's 2 times pi times r, which is 1 in length. And if I were to describe this entire circle as a radian measure, that's going to be 2 times pi times 1, the arc length, divided by the radius, which is also just 2 pi. So there are 2 pi radians in the circle. You remember the meme with the African American gentleman in the old-fashioned suit where he says rent is too dang high? It was a popular meme about 2016, might be before your time. But one way to remember this is the number of radians in a circle is too dang high. Well, I'm making it PG rated, Justin. So 2 pi radians in a circle. And again, radians are built into the circle in a way that degrees will never be. Degrees always inferior as a consequence. Even though they're inferior, we just can't let them go. We hold on. Because it's what we know. We're like in a person in a bad relationship. We don't want to leave because we're comfortable. Special triangles. So there are 2 special triangles that are important to us in this section. They are the 30-degree, 60-degree, 90-degree triangle, which has the ratio of 1 to 2 to the square root of 3. So opposite the 30-degree side is 1 unit. Opposite the 60-degree side is the square root of 3 units. And opposite the right angle is 2 units. So this ratio will always exist in a 30, 60, 90 triangle. So every triangle. So if I know some arbitrary 30, 60, 90 triangle, has 4 for this side, well, then I know this is 8. And this is 4 on the square root of 3. You see what I mean? So this ratio will persist in every case. This is the fundamental case, most simple case. This is an arbitrary case.
So this side, the side kind of floats into the water?
The ratios persist. So if triangles are similar, you remember the difference between similarity and congruity? So congruity means exactly the same. Similar means has the same angles. So any similar triangle, in other words, any triangle that has the same angles as this, will have the same ratios. So the hypotenuse will be twice as long as the shortest side. And the longest side will be the shortest side times the square root of 3. So the similarity tells us the ratios persist. Now, they won't be exactly the same, but they will have predictable ratios. Questions about this? All right, cool. Another, and remember, similarity is that symbol there. So any similar triangle will have those ratios. Second one we're going to discuss, 45 degrees, 45 degrees, and 90 degrees. 1 to 1 to the square root of 2. So if I were to consider some similar triangle, in other words, a triangle in which I had the same angles, and let's just say I knew this side was 8, well, then I would know this side is 8, and this side is 8 times the square root of 2. It's a way for us to have a whole family of triangles that we can instantly know everything about. So solving these triangles is trivial as a consequence of their special cases.
then that one's kind of the same until it's like square root of 2 by the side.
Yeah, so you've got here the general case, the case we'll use as sort of the parent of the special triangle family. And here we have children or certain individual cases. And because of that similarity, we know this side to this side is going to equal this side to this side. In other words, the ratios will persist. Good question, Rachel. Other questions? All right, cool. So the unit circle, oh yeah, boys, it's time. So the unit circle, and I'm going to construct the first quadrant of the unit circle.
No, we need to draw this.
I would sketch this if I were you. Yeah, you would want this in your own handwriting. So these unit circle, the definition of the unit circle, the reason why we call it unit circle is radius equals 1. So the unit circle means the radius is 1. And do you see how that makes our life easy? Because when we divide by the radius, we're just dividing by 1, and it's a trivial exercise. So the reason why we choose the unit circle is to make our lives easier. So what we're going to do is describe the sine and cosine of these common angles. So for every point on this unit circle that is swept out by one of these special angles, there's going to be, that point is going to play an important role. And all we need to do is consider one of the triangles to understand why. So I'll consider this triangle. So if I come out to that point, 30 degrees on the unit circle, then I drop down to the x-axis, and then I come back to the origin here. It creates this triangle. It's got 30 degrees here, 90 degrees here, and it's got a point here, which is the x and y coordinate on the unit circle. So this length here is going to be your x. This length here is going to be your y. And then this radius, well, the radius is always what in the unit circle? 1. So this side of the triangle, I know, is 1 unit in length. Now, so I know some things about this triangle. First of all, this is 30, and this is 90. What does this angle have to be? 60, indeed. They have to add up to what?
180.
Yeah. Come on, you guys remember that. So we've got a 30, 60, 90. And we remember that the parent of sorts of that special triangle family had these ratios. So I know the ratio of corresponding parts has to be equal. Do you see how 1 corresponds to 2 and y corresponds to 1?
Yeah.
So I can set up this relationship. 1 over 2 has to equal y over 1. In other words, y equals 1/2. And then I also know, I need to use a different color, man.
Wait, what is that? The 1 over 2 is equal to?
All right, so once again, from the top, these triangles are similar.
Yeah.
They both are 30, 60, 90. So I know the ratios of their sides must be equal. In other words, they're expanded or contracted in some way, but it's the same for all sides. So 1's ratio to 2 has to be the same as y's ratio to 1. Hence this equation.
Okay.
Now, the same is true. 1 to 2 has to be equal to x divided by the square root of 3. And so if I multiply both sides by the square root of 3, I get radical 3 over 2. So all of this has given us this point on the unit circle. Radical 3 over 2 comma 1/2. Now, why do we care so much about the unit circle? Well, think about it. Remember the ratio for the sine, Jesse. What is it? Blank over blank. Remember old Chief Sokoto?
Opposite of the bottom.
Very good. And do you see how the opposite over the hypotenuse is y over 1? And so this value is the sine of that base angle. So that's the sine of 30 degrees. And do you remember the ratio for cosine, Colin?
Cosine is adjacent over hypotenuse.
Well, that's x over 1. And so this, the x coordinate, is the cosine of 30 degrees. And so in every case, for the points on the unit circle, they are the cosine and the sine of that base angle, respectively. So every point on the unit circle is the cosine of that angle for the x coordinate and the sine of that angle for the y coordinate. So the reason why the unit circle matters is the points on the unit circle are the cosine of alpha and then the sine of alpha, where alpha is the base angle. So all the points are the cosine and the sine for the x and y. So it allows us to know a lot of trig values very quickly. Now, some of these points are kind of trivial. So the quadrantal points, in other words, 0, 90, 180, those are trivial.
You scroll down a little bit, I didn't get all that.
You're welcome. Okay, so these quadrantal points are going to be pretty easy to find because I'm just going 1 unit out here in the x direction. So that's going to be 1 comma 0. And here I'm going 1 unit up in the y direction. So 90 degrees is 0 comma 1. And in fact, we've really already found 60 degrees too. Do you see how if I were to color in the triangle for 60 degrees, it's the same as the green triangle, flipped the other way? It's also a 30, 60, 90. It's just the x and the y are interchanged. And so we need to do no additional work to know that point. We just flip the x and the y. So that is 1/2 comes square root of 3 over 2. And again, this is cosine of 60 degrees, sine of 60 degrees. So we've got one little bit we need to find left. And I'm going to come down here in the nether regions and work on that real quick. Appreciate you guys taking careful notes. Always want to facilitate that. So don't be afraid to do what Rowdy did and ask me to show more of the screen. Okay, so this triangle now, you may already predict that's the other special case because it's 45 degrees, 45 degrees, 90 degrees. How long is its hypotenuse here? Remember that it's a radius. What are all radii in the unit circle? 1. And furthermore, I know that all 45, 45, 90 triangles have the ratio of 1 to 1 to the square root of 2. So this is sort of the parent of all 45, 45, 90 triangles. This is that special case. We've got an x coordinate and a y coordinate, and we're concerned about this point. We want to describe this point. So what is x and y? Well, I know 1 divided by the square root of 2 has to equal x divided by 1. In other words, x equals 1 over the square root of 2. But you remember, we don't like radicals in the denominator as mathematicians. You probably had an algebra teacher somewhere along the way that told you about rationalizing the denominator. And so here, that's what we must do. In order to rationalize this denominator, I'm going to multiply top and bottom by the square root of 2. And so I get square root of 2 divided by 2. So, get this. Now, I don't even need to do that again, because what these two angles being the same makes this triangle what kind of triangle? Starts with an I. Isosceles. And what's true about the legs of an isosceles triangle? They're the same. So we can just say that's the same. Now, we have found the last point in quadrant 1. Okay, so, and I'm going to put all this up here at once. Points equals cosine alpha, sine alpha. So for every point, you have a cosine for the x-coordinate and a sine for the y-coordinate of that angle. So question, Bristol, look at this. Tell me what the cosine of 30 degrees is. Feel free to come up and take a closer look if you can't see. Cosine of 30 degrees. What is it? Square root of 3 over 2. Good. Rowdy, what is the sine of 60 degrees?
Square root of 3 over 2.
Excellent. Holden, what is the cosine of 0 degrees? Good. Ian, what is the sine of 90 degrees? Incorrect. It's the y coordinate. 1. Good job. Rachel, what is the cosine of 45 degrees?
Square root of 2. Square root of 2.
Good. And then Colin, what's the sine of 45 degrees?
Sine. Square root of 2 over 2.
Excellent. Any questions about that? See how useful this is? So you can know. Now I could get a decimal approximation with my calculator. I could pull out my calculator and I could say, make sure I'm in degree mode. You'll be changing that mode quite a bit for this chapter, by the way. You'll be going back and forth from degrees to radians. So be conscious of that. So if I were to put in sine of 60 degrees, it would tell me that's 0.866, but that's not the exact value. To know the exact value, I need the unit circle. This is a decimal approximation. I know it is the square root of 3 divided by 2. See how this is superior to any calculator. The human mind is the greatest calculator. Okay, any questions about the construction of the unit circle? From this point forward, I hold you responsible for having the first quadrant memorized. Yes. And as we go forward in this chapter, I will hold you accountable for the rest of the unit circle. Sir?
I'm still kind of confused on how on the 45, 90s,
Mm-hmm.
you got the 2 on as bottom over the square root of 2 over 2. I don't know how you got the.
So we rationalize the denominator. Let me go to. So the question was, where the heck did the 2 come from?
Yeah.
So this is the original formulation. You're squared away on this part, right?
Yeah.
So we took this value, 1 over the square root of 2. We hate this. This is ugly. This has got a radical in the denominator. Why do mathematicians hate radicals in the denominator? Well, long time ago, long time ago, you had to compare values to tables. You see how you need a certain format for that comparison to be valid, so you're not having to constantly manipulate. So just the format they agreed on was rationalization of the denominator. But anyway, no special reason now. It's an archaic reason. But we hate radicals in the denominator. And so we're going to rationalize them. And you rationalize by multiplying by a special form of 1. You see how the square root of 2 divided by itself is just 1? So that's not going to change this value when I multiply by 1. It's just going to make it appear different. So it's changing its appearance, like put a mask on. Mask on. Mask on. Mask on. Anyway, so 1 times the square root of 2 is the square root of 2. Square root of 2 times the square root of 2, by definition, It's 2.
Okay.
That help you out, Colin?
Yeah, so you just wanted to so
Say again, sir?
is to get rid of it, and by canceling out, that's how you got the 2. Okay.
Yes, sir.
So you like basically multiply it by the base? Like base together?
Yeah, whatever this radical is that you want to get rid of. If you multiply by that value, the result will be rational. We still got an irrational in the numerator, but for some reason that's okay. We're not sweating that one in the top.
Yeah.
You know, it's like that one is not a concern. Okay, so anyway, this is the first quadrant of the unit circle. Once again, I expect you guys to know this. Going forward. So let's find some exact values of 6 trig functions. Here we have the angle theta, and we want to find sine of theta, cosine of theta, tangent of theta, cosecant of theta, secant of theta, and cotangent of theta. Those are the 6 trig ratios. Sine, remember, is the opposite, which is 33, divided by the hypotenuse, which is 65. The cosine is the adjacent, which is 56, divided by 65. The tangent is the opposite, divided by the adjacent, 33, divided by 56. Opposite over adjacent, TOA. Cosecant, remember, chosha cow. So chosha cow tells us that the cosecant is the hypotenuse over the opposite. So I can just, if I write it in this way that I wrote it here, I can just start flipping the ratios for the second half. 65 over 33. And then secant is hypotenuse over opposite. 65 over 56. And then cotangent, 56 over 33. Oh yeah, boys. We're doing some trig now. We have departed the realm of algebra and entered the realm of trigonometry. How does it feel?
I do that now. I remember.
So easy, you're suspect of it?
What if you don't have like a big sheet of paper, just a big unit circle, like a surrounded?
Well, in years past, I have required that, Jesse. This year, with the in-home, you know, it's going to be trivial for me to give you a unit circle quiz because you could just look it up on Wikipedia or whatever. So I would if I were you, Jesse, but I'm not going to require it in the same way I have in years past.
Could you do it like
Yeah, I'm going to post it. I'm going to post it.
It's like a full one of these?
Yeah, I'm going to post it. Every value on the unit circle derives from what I demonstrated. All the calculation is complete. The rest of it just uses the symmetry of the circle. So we'll describe that in more detail tomorrow. So find the exact values of the 6 trig ratios here. This one's for you. I'll give you about 5 minutes. Well, say about 2 minutes to complete this one. That's too small. Let me enlarge. Computer, enlarge. Just kidding. Boom. Remember to write ratios in their simplest form. In other words, you must reduce to be correct. Once again, that is because you want to be able to compare values to tables in case you get transported to Middle Ages Europe. Like a Connecticut Yankee in King Arthur's Court, famous Mark Twain story. He wowed the locals by predicting an eclipse and was named their wizard. It's Connecticut Yankee. Mark Twain, a great American thinker. Really had a wonderful mind. If you haven't read his work, you should. Question in? Oh, I see. $16.
Yeah.
Once again, we're working with theta. All right, Ian, what's the sine of theta?
12 over 20.
So opposite over hypotenuse, 12 over 20.
Yeah.
And then you reduce that to what?
3 over.
Excellent. What about cosine of theta, Holden?
4 over 5.
Say again?
4 over 5.
Very good. And then what about tangent of theta, Jesse?
3/4.
Yep, 12 over 16, which reduces to 3/4. What about cosecant, Rowdy?
5/3.
Very good. What about secant, Colleen?
5/4.
Excellent, sir. Then last but not least, Bristol, what's the cotangent? Handy shortcut is to flip the tangent.
16 over 12.
Divided by 4.
4 over 3.
Very good. You see what I mean about the handy shortcut? The relationship between these functions and their reciprocal. Okay, so using one trig value to find others. This is an important skill. So we've got sine of theta equals 1 over 3. And we want to find the exact values of the 5 remaining trig functions. So this is the first time, but certainly not the last time, you're going to see me use something called a reference triangle. So I'm going to create a triangle that is not exactly the same as our real triangle, but it's going to stand in for it. So I've got a base angle theta, and I know the sine, in other words, the opposite to the hypotenuse has a ratio of 1 to 3. I can now use the theorem of Pythagoras, the Pythagorean Theorem, to know that this is 1 squared plus, we'll call this one b squared equals 3 squared, so 1 plus b squared equals 9. My homeboy's got to hit his jewel real quick. Subtract 1 from each side to get b squared equals 8. And b, therefore, ignore the negative result in this case. So we're not worried about plus minus in trigonometry problems because we're talking about distances, and distances are only ever positive. So because of that context, I know not to use the plus minus in the square root property, just the plus, just the primary root in this case. So the square root of 8 is the square root of 4 times 2, or 2 on the square root of 2. So I have 2 on the square root of 2 for this side, which means the cosine of theta is going to be 2 on the square root of 2 to 3. The tangent of theta is going to be 1 over 2 on the square root of 2. And if I rationalize, I'm going to get square root of 2 over 2 times the square root of 2 times the square root of 2, which is 4. And then the cosecant is going to be 3 over 1, which is just 3. The secant is going to be 3 divided by 2 on the square root of 2. So if I rationalize, that's 3 on the square root of 2 over 4. And then finally, the cotangent of theta is 2 on the square root of 2 over 1, which is just 2 on the square root of 2.
I think that, yeah, it's the same thing that we did with the like signs.
Actually, I don't like that pink. It's too bright, too dark. There we go. What were you saying, Colin?
I was just coming to the conclusion that it's the same thing to cancel those out as we did on the to cancel it out. So that's how you got the thing on the top instead of the bottom. So it's not.
Yeah, the rationalization of the denominator. Good observation, Colin. That is indeed the exact same process. Okay, so using one trig value to find others. Questions about this technique? Or thoughts or comments? Everybody, you guys got this? I just taught you trig in 50 minutes, sir.
On the sheet.
Yes.
The trig, why did you give us one?
So on the bottom, I have 2 on the square root of 2 originally. I multiply that by the square root of 2 to rationalize. In other words, to get a result that does not have a radical. The square root of 2 times the square root of 2 is 2. So 2 times 2 is 4. Good question. Other questions? All right, boys and girls. Let's go on to example 3. Special angles, we've already done this part. This is how you find those first few values on the unit circle, 30, 45, 60. Find the value of x. Round to the nearest tenth if necessary. So here we've got an angle, and we've got 2 sides. With respect to the right angle, with respect to 35 degrees, that is the adjacent and the hypotenuse. So if I want to talk about the adjacent and the hypotenuse, what trig function should I use? Cosine. So if I were to say the cosine of 35 degrees, do you see how that is 7x divided by 7? And so if I multiply both sides by 7 here, 7 times the cosine of 35 degrees equals x. Now that's exactly correct. However, that's not very useful. What if I were to go into Lowe's and say, I need 7 times the cosine of 35 units of lumber? They're going to be like, what the heck, dude? So we'll convert it to a decimal. And this part of the mathematics that we're studying, I use frequently in my home projects. So I build furniture, and I build decks and do all that sort of things. And I frequently use angles. In fact, I recently did a project where I created a weight set for myself. And I had to use a lot of trigonometry to make that work. And it came out perfect, surprisingly perfect. Okay, anyway, back to this. 7 times, we're already in degree mode. 7 times the cosine of 35. If you ever get a weird answer, way different from mine, you're probably in the wrong mode. 7 times cosine 35 is about 5.7 units. What units? Well, we're not told, so we're not worried about it. My homeboy, he's high on Joule now. Nobody talk to him.
He's retarded.
Find the missing side link. Look at this homeboy. He runs like this. So a competitor in a hiking competition, who knew such a thing existed? He's going to climb up this inclined course as shown to reach the finish line. And he's going to run like this the whole time. Determine the distance in feet that the competitor must hike. In other words, what the heck is this? So I've got 48 degrees, and deep under the earth here, this is 1 mile. So what does this have to be? So what we've got is, again, the adjacent and the hypotenuse. So we're going to use the cosine. Cosine of 48 degrees is going to equal adjacent 1 over hypotenuse d. So we've got a little bit more algebra here to do. If I multiply both sides by d, and then divide both sides by the cosine of 48, I can get my answer here. So 1 divided by the cosine of 48 degrees is about 1.49. What does it say to the nearest? Oh, it wants it in feet. Oh my heavens. So we got to multiply that by 5280. 7890.8. So let's go to the nearest foot. 7891 feet. And that little single tick mark indicates feet. It's kind of a shorthand way to say feet.
So when you're adding in a degrees, you don't do like 0.48 or do you just?
No, just 48. For the calculator, yes, just 48. You don't convert to a decimal. It's not like a percentage or anything in that respect. It's always going to be that whole number of degrees. right. Questions before we move on? We're going long today. That's okay. Inverse trig functions. Remember, they undo what the function does. So let's do an example with an inverse trig function. So we want to find the measure of theta. So this time we've got the sides, we need the dang angle. So with respect to this angle, I've got the opposite and the hypotenuse. So what kind of trig function discusses the hypotenuse and the opposite? Indeed, so the sine of theta is going to be that 12 over 15.7. Now, I don't want the sine of theta, I want theta. So if I take the sine inverse of both sides, this is going to be just theta. And we'll approximate that value with a decimal. Seems like we covered a lot of stuff today, man. Sine inverse 12 divided by 15.7. And the trig inverse functions have a very limited domain. So if you ever get a domain error, you screwed up your algebra somewhere. It's a pretty convenient check against mistakes, in fact.
How do we change it to degrees on a calculator?
If you hit mode, and then you'll see this third option down, you select the one you want and hit enter.
Oh, I see.
And the darkened one is the selected one. So in this case, 49, and what are we rounded? To the nearest degree. So that's 50 degrees to the nearest degree. Oh yeah, baby. You ever learn so much in one day?
Not usually.
I think I'm just going to retire now.
Yeah,
I've hit peak Chad. My first name is Chad. I'm an actual Chad, not a pretend Chad, not a pretend internet Chad.
The real thing.
Indeed. You can say that without an ounce of sarcasm. So last one we're going to talk about here, angle of elevation. You got a chair lift at a ski resort. You guys been skiing?
Yeah, I actually have tried.
You know, when you get on the chair lift, you got to like move, and it's dangerous if you're not careful, especially if you're unfamiliar with the skis. But anyway, because the chairlift doesn't stop, it just goes.
That's not just ski forward.
It's easy to do. In fact, if you want some comedy and you're kind of tired of skiing, just sit and watch people get on and off that thing. It's pretty hilarious. Okay, well, anyway, this chairlift is at a ski resort, and it rises at an angle of 20.75 degrees while traveling up the side of a mountain and attains a vertical height of 1,200 degrees when it reaches the top. How far does it travel? In other words, what is the d? So we've got the opposite and the hypotenuse. We want the sine here. Sine of 20.75 equals the opposite over the hypotenuse. Again, the algebra is a little funky here. Multiply both sides by d and divide both sides by the sine of 20.75. And I get the following, which I'll approximate. And we'll just go to the nearest foot because that's what we've been doing. Boom. 3387 is the nearest foot. That's a long lift, man.
Are you talking about those things that carry you up to the?
Mhm.
Yeah, at the top of the slope.
I wouldn't get on that thing.
And this is in feet. Don't forget your units.
You can get stuck in.
Applied mathematicians are pretty anal about units. Okay, so now a brief assignment. Oh, goodness. Just don't know why. Microsoft products take 16 years to start up. It's almost like Microsoft just stopped trying at some point.
I just gave up on this.
Indeed.
That's fine.
So your task is going to be page 227, problems 2, 8, 10, 16, 18, 20, 22, 27, 33, 46. This seems like a lot, but these are pretty brief. This will be due on Monday at 11:59. Guys, you all push at 11:59. You don't want to know how many submissions I get at like 12:02. It's not just you, Rachel. Like 10 people did that last night.
Yeah, last
can
night,
vote.
I like.
Oh, I tried to
It's
do
kind
mine.
of like,
I tried to do mine the day they're assigned, except over like a fence and stuff. I tried to work on
I was
like each
not-
day.
Yeah, I was not expecting to be silent there in one day, and I was like, just trying to shove it all in.
It's okay.
We got there though, we finished.
Indeed.
Mr. Schneider, I actually had a question about one of my homeworks.
Sure, buddy.
So for chapter 3.5, the last question, it gave you the elevations
Mm-hmm.
and the boiling point of the water. And that problem is to linearize a